In this video, I want to just quickly look at some strategies for determining a good choice for a convergence test when doing these series. Because remember, we're interested in determining when a series converges or diverges. I'm not going to do all of them, but I am going to do a selection. We're just going to talk about an appropriate test. We're not going to talk about how to do the test. You can go back and look at previous notes for that. So let's look at 1b here. So 1b, we have 1 over 5 to the n plus n. And my thought is that, well, the top is 1, and the bottom is an exponential 5 to the n plus some positive number n, because n goes from 1 to infinity. So I'm thinking this should behave like, in some sense, 1/5 all to the n. And so that's what I'm going to use to compare here. 1/5 to the n. Since the denominator here is bigger, I know it's going to converge. And the reason I saw that is because I'm looking here and I'm thinking the term in the denominator with the highest growth rate is this exponential one. So I'm thinking of a series to compare with a series that doesn't have the other inconsequential, in some sense, terms in it. Let's go and look at a few more. If we look at 5b here, you'll see that we have a term all to the nth power. So I'm thinking for this one, for 5b, I notice that I have a term that's all to the nth power. So a reasonable test to think at first is the root test. And thinking ahead, well, the root test kind of gets rid of something to the nth power. So what would the limit of this look like as n goes to infinity? Well, the bottom has a bigger degree than the top, so this limit would be 0. So I'd get something that isn't 1, so the root test would give me a definite conclusion. Let's keep going here. In fact, let me just erase this. And then I will keep scrolling. Let's quickly talk about 6b n ln n in the denominator and 1 in the numerator, so 1 over n ln n. And my first thought is that, well, looking here, ln is kind of a tricky function to deal with in terms of multiplying and comparing. So maybe a good choice here would be the integral test, since I know if I make the substitution, say u equals ln of n, then I know I can take out a 1 over n to be able to make that substitution. So I'm going to do an integral test with u equals ln of n. And to be completely precise, really it should be ln of x, where there's that embedded continuous function, so we could do calculus on it. And let's keep going here. So let's look at a few more here. And I'll erase this in a second. Let's look at 14 here, just as another one. So here, the first thing that I notice is that, well, again, we have these powers of n in the numerator and denominator. So I would rewrite this as n squared over 1 plus n cubed all to the power of n. And then thinking about that, I'm thinking of a root test here as well, since I have a term all to the power of n. Okay, let's look at a few more. Let's look at maybe 16. So 16, first thing I notice is that this is indeed an alternating series. So I'm thinking two choices here. And in some sense, either choice would be totally fine. But for this guy here, I see that -1 to the n minus 1. So I'm thinking that this is an alternating series, so that's great. So one choice here is to use the alternating series test. And you can see that this is indeed decreasing and the limit is going towards 0, since the denominator grows much faster than the numerator. Exponentials grow faster than polynomials. But another test you could do, and you should be able to get an outcome that gives you convergence, is the ratio test. And the reason that I say that is because I notice this 4 to the n in the denominator here, and I'm thinking, well, the ratio test talks about absolute convergence, so I'm not worried about this -1 to the n minus 1. And if I do the ratio test, you'll find, I believe that you'll get a limit of 1/4, which is less than 1, so you'll get convergence as well. For 17, this one, I'm definitely thinking the ratio test because I have exponentials and factorials, and they cancel out nicely in the ratio test. The alternating series test might be a little bit harder to show since you have this pi to the 2n over 2n factorial, so it would be a little work to indeed show that this is indeed decreasing. And also to show that the limit is 0, since we can't easily embed this into a continuous function, it might be a little bit difficult. For 19 here, I'm thinking that this is the sum of two series. So I can write this as 1 over n cubed plus 1/3 to the n. And I'm thinking both of these converge, so I can say immediately that since both converge, then the sum converges. So I can just do them separately. Let's keep going. And I'll erase this stuff in just a second. Let's look at a few more. Let's erase this. And let's look at number 22, for example. First thing I notice with this is that we have a sign here. I'm thinking of sign like a constant between -1 and 1. So my initial thought here is, well, maybe I should try and show absolute convergence. So I'm going to think to try to show absolute convergence. So maybe we'll look at the sum of the absolute value of sine of 2n over 1 plus 2 to the n. And then I'm thinking, well, again, this is definitely less than 1 in absolute value. In fact, it's going to be between 0 and 1 in absolute value. In my denominator here, this is going to behave a lot like 2 to the n. So I'm going to compare this to 1 over 2 to the n, knowing that sine of 2n in absolute value is always less than 1. And 1 plus 2 to the n is always greater than 2 to the n. So my denominator is greater, my numerator is smaller, so I know that each term in 1 over 2 to the n is smaller than the terms in sine 2n over 1 plus 2n. And since I can show that this converges by the comparison test, I know this converges. And since I showed that this series converges absolutely, I know that without the absolute value, this much must converge as well. Quickly, let's look at 24. So with 24 here, I'm thinking, well, I have a ratio of 2 polynomials here. So let's compare it to something where the terms that aren't leading aren't involved. So I'm thinking of this along the lines of the square root of n to the fourth, which is n squared over n cubed. So I would probably compare this to n squared over n cubed, taking the biggest degree of both here. And here, the direct comparison test won't work. The numerator here is actually bigger, but this term isn't going to matter too much. So if you can't get the direct comparison test to work just for small fiddly reasons, you should try using the limit comparison test here. Let's look at the one below. So immediately I see a bunch of things multiplied together here. So my thought is I want them to cancel, so I think a good choice for this is a ratio test. Since hopefully you'll get lots of cancellation in both the numerator and denominator and just be left with one term in the numerator and one term in the denominator, and then you should be able to easily take the limit. I believe the limit will be 2/3, so this indeed does converge. And let us keep going. I'm going to erase everything here. And we'll scroll up. Let's quickly look at 29. So 29, in fact, I should have really been doing this with all series that we talked about so far, but I've been doing the test for divergence in my head before I do anything. Is the limit of the terms actually 0? If it's not, then I just know automatically that the series diverges. So here, I know that cos of 0 is actually 1. So the limit as n approaches infinity of cos of 1 over infinity, which is cos of 0, is going to be -1 to the whatever times 1. So here, just using the test for divergence, I know that the series is going to diverge since the limit of the term isn't going to be 0. And remember, that's something that you should really check before you do any of these. You should always think the test for divergence. Looking at 30 now, I see I have 1 over 2 plus sine k. And my immediate thought is, well, I'm thinking of sine of k like a number between -1 and 1. So here, I know that if sine of k was always -1, then this term here would be 1. And if sine k was 1, then this term here would be 1/3. So I know that my an is always going to be between 1 over 2 plus 1 and 1 over 2 plus -1. So that's between 1/3 and 1, which tells me that the limit as n approaches infinity of an can in no way equal 0, since it's bounded always by a third and 1. So this is another example of using the test for divergence. So this doesn't equal 0. Let's look at 31 now. So we have tan of 1 over n. And remember, tan is the same thing as sine of n over cos of n. And you can think of, well, what does the test for divergence say? Well, this says that we have sine of 0 over cos of 0, so that's 0 over 1, which is 0. So the test for divergence is passed, so this doesn't automatically diverge. So we have to think of a test to do. So let's quickly talk about our tests. Well, the alternating series test obviously doesn't apply here. This isn't an alternating series. I don't particularly know the antiderivative of tan of 1 over x dx, so the integral test might be a bad choice here. The ratio test and the root test I can't see working easily unless there was a really nice trig identity that I can't think of off the top of my head. So in those situations, if it's kind of difficult, you just might have to try something and try some sort of comparison test, and usually a limit comparison test is a good way to go. So let's try a limit comparison test. So this one is fairly difficult in the way that it's not quite obvious what to compare it to. So you might just have to do some trial and error, but some good choices are, of course, p-series or geometric series. And I think p-series would be a better choice here. And the reason that I say that is the following. I could imagine that if I was doing a limit comparison test and I would want to use L'Hopital's rule, I would take the derivative of the inside of this, which is 1 over n. And if I take the derivative of that, I get something along the lines of negative 1 over n squared. And I'm talking about a function that embeds this, so a continuous function, tan of 1 over x, say, but the same idea. And thinking that a polynomial is going to kind of come out of this when I take the derivative, maybe I should compare this to some sort of polynomial. So typically, you want to try both 1 over n and 1 over n squared first, since we know 1 over n diverges and 1 over n squared converges via p-series. So it's kind of tough to tell here, but it looks like if you had time, it might be worth exploring this term by term almost. So if you calculate A1 here is going to be roughly 1.55, whatever. But A2 is going to be roughly 0.54. A3 is roughly 0.34. A4 is roughly 0.26. A5 is roughly 0.20. A6 is roughly 0.1, let's say 68. A7 is roughly 0.143. And looking at these values, you could check, are these close to either 1 over n or 1 over n squared? A1 isn't really close to anything, but this is something along the lines of, this is close to 1/2. 0.34 is close to 1/3. 0.26 is close to 1/4. 0.20 is close to 1/5. This is close to 1/6. This is close to 1/7. So it looks like after some experimentation, it's roughly 1 over n. So maybe you'd want to do a limited comparison test with 1 over n. So if you're not sure what to do, just calculating some terms and seeing if you can kind of notice that they're close to another series that you know really helps you decide what to compare to. Okay, this limit comes up quite a bit in some of our problems, and I just want to remind you guys of it. So, this is kind of the definition of e to the a in fact. So if you have 1 plus whatever value a you like here over n, all to the power of n, the limit is e to the a. And let's see if we can show this. So I'm going to call y this function, and let's embed this into a continuous function so we can do calculus on it. So we'll do 1 plus a to the x over x. Remember, n we're thinking of as just discrete counting numbers, and x we're thinking of as real numbers where we can do calculus, we have continuity. So we have something of the form, if we take the limit as n approaches infinity, we have something of the form 1 over a to the infinity. So this is like 1 plus a over infinity. So that's 1 plus 0 to the infinity. So 1 to the infinity, which is one of our indeterminate forms. So the limit as n approaches infinity of 1 plus a over x to the x is of the form 1 to the infinity, which is an indeterminate form. And we can kind of see that this is an indeterminate form if we kind of perturb this 1 just a little bit. That's always a good method to see if this is indeed an indeterminate form. If we subtract the smallest bit from 1, so if we have 1 minus some small value, which we'll call epsilon, to the infinity, and epsilon is just really close to 0, but it's still positive. It's still a number, it's just very small. Then the limit of any number that's less than 1 to the infinity is going to be 0. So the limit goes to 0 in this case. But if we add epsilon, we get some number bigger than 1 to the infinity, and in that case, you get infinity. So when you have values that don't jive, when you perturb them, so when you have some limits with infinity and you kind of perturb the finite part and you kind of get different values depending on how you've perturbed it, this is a good clue that this is indeed an indeterminate form. So what we're going to do here is we're going to set this equal to y. And now I'm going to take the ln of both sides. And if I take the ln of both sides, that lets me bring down my exponent. And that's kind of the key here. So it's x times ln of 1 plus a over x. And I'm thinking if I take the limit of this now, if I take the limit as n approaches infinity of x ln of 1 plus a over x, well, I'm going to get infinity times 1 plus a over infinity, so that's ln of 1, which is 0, so I get infinity times 0, which is another indeterminate form. So I want to write that as a fraction. So this is like, let's say, equals, in quotation marks, infinity times 0. So I'm going to rewrite this as the limit as n approaches infinity. And I want to have one of these, I want to turn this multiplication into a division. So we'll get something like 0 over 0 or infinity over infinity, and then I can use L'Hopital's rule. So the easiest way to do this is to make, instead of multiplying by x, I'm going to divide by 1 over x. So this is going to be the same as the limit of ln of 1 plus a over x, over 1 over x. And now this is of the form 0 over 0. I'd say I have ln of 1 if I quote-unquote plug in infinity here, over 0, 1 over infinity. And I'm being a little sloppy. It's actually not as n approaches infinity. All of these, since we introduced x, all of these should be as x goes to infinity, not n going to infinity. So let me change those. I think that's all of them here. Okay. So let's use L'Hopital's rule. In fact, I'll start a new slide and we'll do it. And the reason I like L'Hopital's rule working here is because I know the derivative of ln of something is 1 over that. So this will kind of immediately get rid of this ln. It will change it to a polynomial of what's on the inside, and that should be able to help me out here. So let's use L'Hopital's rule. I like to put an LH to say I'm using L'Hopital's rule, because otherwise it's kind of unclear to the reader what you're doing here. So let's take the derivative of the top. So we're going to get 1 over the stuff in brackets. So we're going to get 1 over 1 plus a over x times the derivative of what's inside the bracket. So that's going to be negative a over x squared. And we're going to divide by the derivative of the bottom, which is just negative 1 over x squared. So we had to use the chain rule in the top part, and the bottom part was no problem. We just took the derivative. So we can see some cancellation happening quite easily here. So let's cancel as much as we can. We get this negative 1 over x squared canceling with this negative 1 over x squared. So we're just left with a there. So I can rewrite this as the limit as x approaches infinity of a over 1 plus a to the x. And let's see what happens if I let x go to infinity now. Well, if x goes to infinity, I get 1 plus a over infinity. So that's 1 plus 0. So this term, as x goes to infinity, this whole thing goes to 0. So this is just going to be a over 1, which is just a. But remember, that was ln of y. So we have ln of y. Or I should say the limit. Let's write that a little more accurately. The limit as x approaches infinity of ln of y is a. So if we're looking for what y is, remember y was our original function, well, we just need to use these as exponents for e to get rid of the ln. So let's do it. So this is the same thing as the limit as x approaches infinity of e to the ln y equals e to the a. And of course, our e and ln cancel since they're inverse operations. So we get the limit as x approaches infinity of y, since e and ln here are inverse operations. They undo each other. So that equals e to the a. So if that limit ever comes up in some series problems, then you'll know, hey, immediately, maybe you had something along, let's say you did a, you had something along these lines, the sum as n equals, let's say, 1 to infinity, and I'm just kind of making this up, 1 minus 1 over n to the power n squared. Let's say something like that. Looking at that, maybe the root test would be appropriate here. So I don't have to worry about absolute values since everything's already positive. So I'm going to take the limit as n approaches infinity of 1 minus 1 over n to the n squared, and then I want to take the nth root of that. So this gives me the limit as n approaches infinity of 1 minus 1 over n, and then I have n squared divided by n, so that just becomes to the n. And I'm going to write this in a form where it looks like what we just did. So the limit as n approaches infinity of 1 plus negative 1 to the n, or over n, all to the n. And we know that this is going to be e to the negative 1, which is the same thing as 1 over e, which is definitely less than 1. So if you remember, the root test tells us that if the limit here as n approaches infinity is less than 1, we know we have convergence. So hopefully that was helpful in terms of figuring out some various series problems.